Hi, everyone. My name is Timothy Chu. I'm a fifth-year PhD student under Dr. Gary Miller. And today my talk is on functions that preserve Manhattan distance. This is joint work with Professor Miller at Carnegie Mellon, a student at MIT named Shyam Narayanan, and Mark Selke, a PhD student at Stanford. So before I get into the core puzzle of this talk, I'll start with a definition for those of you unfamiliar. What is a Manhattan distance? This distance is also known as a taxicab distance or L1 distance. And very simply put, if you have 2 points, the Manhattan distance, you can compute by taking the difference of their x coordinates, the difference of their y coordinates, and adding the absolute value. Now, this generalizes in the natural way to arbitrary dimension. So that's the definition of a Manhattan distance. So the core motivating puzzle that our talk will focus on is the following. Given any n points in any dimension and for any n, let's say you compute the n choose 2 Manhattan distances between each pair of points. Next, you're going to do something crazy, like raise them all to the 2/3 power, or really any power between 0 and 1 can work. Now I claim that the result is always a Manhattan distance. That means that the n choose 2 distances I get after raising it to the 2/3 power can themselves be realized as a Manhattan distance between n new points. Why on earth would this be true? A priori, there's no reason to believe anything like this whatsoever, and yet it happens to be a true statement. So before I dive into the details of the proof or the roadmap, let's just try a very simple example. Let's say you're given 3 points on a line at 0, 1, and 2. And you compute the Manhattan distances between each pair of points. Next, you raise each distance to the 2/3 power. And I want you to find 3 points whose Manhattan distances match these power distances. Now, I'm just going to give everybody in the audience a couple minutes to think about this. If you have this in advance, like if you already figured it out, maybe you can try it for 4 points. But I just want to give people 2 minutes to get their hands dirty and also ask any questions they have about the setup in case it's confusing. So yeah, feel free to break out a pencil and paper, try to work this out. This is just a very simple example, an illustration of our larger problem.
Wait, Tim, when you say align, is this an axis aligned line?
Oh yes, sorry, axis aligned line. Good point. This is just the one-dimensional line.
Do I have
to just about 30 more seconds. I just want people to really get their fingers a little bit dirty, grappling with this problem a little bit, trying to figure out where the core difficulties are.
Do the new 3 points also have to be on the line?
No, the new 3 points can be in any dimension. That's a good question.
Yeah.
So Tim,
Right, just a couple more
how many dimensions do we need to put it in?
You can choose however many dimensions you can do it in. So if you need 100 dimensions, you can use 100. You only really need 2, but if you need 100, you can use 100. All right, about 10 more seconds, just so people have time to ask questions about the setup and think a little about this problem. It's okay if you didn't figure it out. I just wanted you to get you thinking about this kind of question. Cool. So I'll just be going over a quick solution. Let's say your pairwise distances are 1, 1, and 2, because those are the Manhattan distances between these 3 points on a line. You raise them to the 2/3 power. These are your power distances. And I claim that the following embedding will work. Now, this might look like a mouthful, but you can just compute the distances between A and B, quickly verify the Manhattan distance there is 1. The Manhattan distance between B and C is similarly 1. And if you compute the Manhattan distance between A and C, you can find that it is in fact 2 to the 2/3, aka the cube root of 4. So I'll just give you about like 10 seconds to stare at this, just because you've already thought about this problem for a little bit. before I move on to the roadmap and the overall structure of this talk.
So I have a question.
Yes.
So is the implication here that there exists, or it's common to have sets of different distances that aren't Manhattan distance sets? Because
yes.
so far you've only been declaring things that are Manhattan distance sets.
Yes. So it turns out, and this will be outside the scope of the talk, but if I gave you a random set of distances, and let's say you even force them to satisfy the triangle inequality,
Sure.
like chances are they will not be Manhattan. And there are many counterexamples for this, some of which I can show after the talk.
Okay, thanks.
Yeah, but that's a good question. You know, you might think every distance is Manhattan. This is not the case. And it's a cool exercise to try and construct a distance or two that is not Manhattan. And in fact, as your number of distance points grow large, number of distances grow large, like basically none of the distances will be Manhattan. Like if you just picked arbitrary distances.
Okay, gotcha.
Great. Okay. So any questions so far? Can we keep going? All right. So in this case, we say that the function f of x equals x to the 2/3 sends Manhattan distances to Manhattan distances. That is, given any endpoints in any dimension d, if you apply x to the 2/3 to each pairwise distance, you will always get a Manhattan distance back. And there's no restriction on the dimension of your resulting Manhattan distance. So the core mystery of the talk, which is what I will address and what you should hopefully come away with, is why does x to the 2/3 send Manhattan distances to Manhattan distances? And in this talk, I promise you a full and mostly self-contained proof of this fact. So before I go on, I should say why this problem is interesting or important. So back in 1937, so a whole like 80 or so years ago, this guy named Schoenberg tackled this problem not for Manhattan distances, but for Euclidean distances. And he worked with a very famous analyst called Salomon Bachner, and also another very famous mathematician you might have heard of called John von Neumann to solve this problem. And this was published in Annals of Math in 1937. That's a problem with Euclidean distances instead of Manhattan distances. It turns out this work, while not known at the time, turned out to be the foundation of all of kernel methods in machine learning. If you've ever heard of a Gaussian kernel, it's built on Schoenberg's work. It turned out to be the foundation of a lot of work with tensors. It turns out to be the foundation of some mathematical field called harmonic analysis of semigroups. It's used in probability theory. It's used in efficient sphere packing by the work of Cohn and Elkies up at MIT and Harvard. Basically, this kind of question, like what functions send Euclidean distances to Euclidean distances, turned out to be an extremely fruitful avenue of exploration. So the natural question to ask was, what if you didn't restrict yourself to Euclidean distances? What if you tried a different set of distances? And here in this talk, we're sort of working out the problem when instead of Euclidean distances, you have Manhattan distances. So just to recap, this problem is sort of interesting because when you use Euclidean distances instead of Manhattan, this turned out to be the basis of a lot of computer science, a lot of mathematics. And when I should say, that work was used recently, I think, in Stock to prove that the sketching and embedding of norms are equal. Anyway, there was a lot of use across computer science and mathematics for this kind of problem. So our work is a simple, self-contained proof that Bernstein functions send Manhattan distances to Manhattan distances. What the Bernstein function? Don't worry about that too much. Just know that x to the 2/3 is an example of one of them. We'll define them near the end of the talk. It's a little bit of a distraction. Now, I should say this was actually known before. If you combine the work of Schoenberg from 1937 and the work of a French mathematician named Aswad in 1980, they figured this out, but the proof they have is fairly intricate. Another piece of our work, which was not known before, was that only Bernstein functions send Manhattan distances to Manhattan distances. Small typo on the slide. This is new. Previously, it was not known that only Bernstein functions have this property. And in general, this is sort of considered the harder direction of our proof. I should say that our talk will focus on the first point because it is more illustrative, and it's just a little simpler. And it will also equip you with all the tools to understand the second point. So again, the core takeaway of this talk is why would x to the 2/3 send Manhattan distances to Manhattan distances? A full proof. And what is the key property of x to the 2/3 that we're using? So without further ado, we also want you to come away with a deeper understanding of the background tools. So the background tools include a deeper dive into Manhattan distances, a known algorithm for how to determine whether a distance embeds into Euclidean distance or squared Euclidean distance. And finally, I promise you a hidden use of the representation theory of the cyclic group of order 2 raised to the n power. So you don't actually need to know any group representation theory or any group theory to understand this talk. But for those of you who do know a little bit of group theory, I'll point out the hidden use of this representation theory in this paper. And one reason I find this result exciting is because, to me, this was the first time I've seen representation theory used to prove theorems about metric embeddings. Great. So let's dive into the background now. Once again, we are trying to solve our core mystery, and I'm just going to go through a little bit of a relevant background about Manhattan distances. We all know the definition of Manhattan distances by now, and I want to give you a quick puzzle, which is very relevant to our proof and also just a general good fact to know, which is show that any 3-point Manhattan metric is equal to a Manhattan metric on 3 corners of some high-dimensional hyperbox. What's a hyperbox? It's just a high-dimensional rectangle. So you can imagine a hypercube, except you can sort of stretch, each axis by however much you want. I'll give everybody a couple minutes to tackle this problem. This is a very key part of our proof. So everyone in the audience, you can have a couple minutes to think about it. If you figured it out, please don't shout it out, just give everyone else time. And if you're bored, try solving it for n points instead of just 3. Feel free also to ask questions in case this puzzle is not clear. Okay, any questions so far? Feel free to keep thinking about it. Are all the definitions on this slide clear?
Yep.
And a hint for anyone who's stuck is you can try to do it for 3 points on a line first. And then you can use that to build up the same thing for 2-dimensional Manhattan distances and so forth. Just give about another minute for people to grapple with this problem. This is, once again, a very core point of our proof. So that's one reason I'm spending a lot of time on this particular section. Once again, if you figured it out for the 3-point case, try it for the n-point case. Okay, about 30 more seconds. Okay, anyone have a solution they want to share? Feel free to volunteer yourself.
I have a solution.
Sure, go for it.
So if we call the 3 distances A, B, and C, then we set up a cube where one side length is A plus B minus C over 2, then another is A plus C minus B over 2, and the third is b plus c minus a over 2. And
Okay.
then we put the 3 points at 3 like non-adjacent corners.
I see. I see.
Or like 3 neighbors of one endpoint.
Sorry. So you're basically saying you can always do this for a three-dimensional cube. Is that correct?
3-dimensional cube as long as the distances, for any distances that satisfy the triangle inequality.
So are you sure you can get an obtuse triangle that way?
I mean, the Manhattan distance. I mean,
Oh, I see. I see what you're saying. I'm sorry. I'm sorry.
we
You're
have
absolutely right.
we have
You're
three
right.
free parameters, so
You're right.
like we'll just be it. Yeah, this will just the plane through the 3 points we use will just look like whatever.
Yeah, you're completely right. I think what was said is you can do this with a three-dimensional box as long as you set your side lengths appropriately. That's true. That'll work from the 3-point case.
Okay.
I'm going to present a slightly different solution. Does anyone else have a different solution than that? And by the way, that'll generally prove that any 3-point distance is a Manhattan metric.
Any 3-point, yeah.
Yeah.
As long as it satisfies triangle inequality.
Right. Anyone else have a different solution? That's a perfectly good solution. It's just not. I'm not sure how you would generalize it for endpoints in this particular case.
Yeah.
Okay, well, I'll just go through a solution I had in mind. I'm sure people in the audience have theirs. Some of you might be shy. So essentially what you'll do, and I'll show it for 3 points in 2-dimensional space, but this will generalize very easily, is I'm just going to do it individually for each coordinate, and then I'm just going to concatenate my coordinates together. So that's one reason I suggested you should do it for a line first. So in this case, let's say we drop all the points. You know, these are heights we drop to the axes. And the distances are labeled as follows: A, B, C on the y-axis and D, E, and F on the x-axis. I'm going to define A prime to be the point A0, 0, because on the y-axis, you know, the point A only really covers the distance little a. And then the next coordinate will be D0, 0. B prime will be the point little a, little b, little c, because that's sort of the interval that ends up covering on the y-axis. And the next 3 coordinates will be little d, little e, and 0, because that's the interval it covers on the x-axis. Okay, what should C prime be in this example? Just anyone, you can just shout it out.
AB0 DEF.
Yep, AB0, DEF for the exact same reasons. And I'll just give you about like 5-10 seconds to verify that these points have the Manhattan distances we want. And moreover, that they are on the corners of a 6-dimensional box with side lengths A, B, C, D, E, and F. You can get away with fewer dimensions, but we're not worried about dimensions for now. Great. Are there any questions on this? This is a pretty simple example, but this will generalize for any dimensions that any number of points are in. So if you have n points in D dimensions, they are equivalent to Manhattan distances on a subset of corners of some high-dimensional hyperbox. And you can use this exact same strategy. Are we clear so far? Any questions?
I had a question, Tim.
Yes.
Are there like first and fourth coordinates actually necessary here, since we're not?
No, they're totally unnecessary here.
Okay.
You don't need them at all. You could just kill them and it'd be fine. But I just have them because it's just a little easier to see what's going on when you have them there.
Technically, doesn't this construction, isn't this really like a 4-point embedding? Because it also succeeds for D.
Yeah, I guess so. That's a good point. Yeah, it succeeds for the point big D on this, which is the origin here. So yes. Any other questions, comments? Great. Even if you didn't understand any of that, the key point is that if I give you n Manhattan distances in D dimensions, I can find, n points in D dimensions and compute the Manhattan distances between them. I could also give you some hugely high dimensional hyperbox, find some subset of those corners of that hyperbox, and those Manhattan distances will be the same as the original Manhattan distances. So for those of you familiar with like metric theory, this is what I said is more or less equivalent to the Manhattan distance being part of the cut cone. Don't worry about it if you're not familiar with those terms. Great. So that's the key lemma in Manhattan distances that I want you to take away from this talk. That will be very important. Next, we'll move on to something a little more complicated, which is how to determine whether a distance embeds into squared Euclidean distance. Now, why do I say squared Euclidean distance? Well, that's just Euclidean distance squared. All the criterion will be a little easier to say for squared Euclidean distance. And you can effortlessly convert this back to a criterion for Euclidean distance. It's just going to have a couple more square roots floating around. Great. So this is some very classical work of Schoenberg from 1935, slightly different paper than the one I mentioned earlier. And the general question is, how can you tell whether a distance, a set of n choose 2 distances, can be realized as a squared Euclidean distance? Well, there's actually a very nice matrix criterion for this. So let's say you have a distance d on a set x, on a set of n points. It's a squared Euclidean distance if and only if the matrix D, where you just fill out D with the distances between point I and point J, has the following magical property, which is that x transpose dx is less than or equal to 0 for all x's orthogonal to the all ones vector. This is also known as the so-called negative type property of a matrix. Here we assume that the distance between x and itself is 0, and the distance between 2 points, is symmetric. But we don't necessarily assume that these points have triangle inequality. Okay, I'll just give everybody about 5 seconds to stare at this criterion a bit. We'll dive into it a little more because this criterion doesn't seem very accessible at first. For example, how on earth could you test whether a matrix is negative type? It's not like you can just plug in all possible values of x. Okay, so how can we convert this into a criterion that we can actually test for? Well, I'll give a sufficient but not necessary condition that will be very useful through the course of our proof. So let's say you have a symmetric matrix D, and you have the additional assumption that D has an eigenvector, which is the all ones vector. Now I claim that D also has all its other eigenvectors. They all have negative eigenvalue. I want you to show that D is negative type. X transpose dx is less than or equal to 0 for all x orthogonal to the all ones vector. And I'll just give people about 10 seconds to try to see this one. This is a pretty simple linear algebra statement. Any volunteers? Making this ridiculously strong assumption about D. It's got an all ones as an eigenvector, and all the other eigenvectors are negative eigenvalue. Show me that D is negative type.
I mean, write it in the eigenbasis and then, write out the quadratic. Okay, so write it in the eigenbasis, like in the expansion of the eigenvectors, and then everything that's orthogonal to 1 won't have the first element, and everything else, will be strictly non-positive.
Right. It turns out that, I'm just going to rephrase what you said. If x is orthogonal to the all ones vector, well, a symmetric matrix has orthogonal eigenvectors, just a basic fact about linear algebra. So if x is orthogonal to the all ones vector, it is a linear combination of my other eigenvectors. If it's a linear combination of my other eigenvectors and they all have negative eigenvalue, then I know that x transpose dx is less than or equal to 0. Okay, if you didn't understand that, just take my word for it that this criterion is sufficient. Do a quick example. Let's say D is the matrix 0, 1, 1, 0.
Wait, why isn't this necessary?
Sorry? Why isn't this necessary?
Yeah.
Well, not all D will have eigenvector of the all ones, right? Like D could have any eigenvectors. I made a pretty strong assumption on what the eigenvector of D was.
Oh, I see. Among Ds that have all ones as an eigenvector, this is necessary and sufficient.
That's correct. If you assume D has eigenvector of all ones is necessary and sufficient, not all matrices D have this property. Are we good? Good? Yes, no, maybe? Okay. I'll just do a quick example here. And once again, we're just trying to understand this negative type property in a little more depth. And I promise you, we'll link back to the original puzzle very soon. So let's say D is a matrix 0, 1, 1, 0. This is eigenvector of the all ones, and the other eigenvector 1, -1 has a negative eigenvalue. Okay, so this is a negative type matrix. Well, what's the associated distance to this? Well, if you have 2 points that are unit 1 apart, this matrix D is the matrix of squared Euclidean distances. So the fact that this matrix is negative type shows me that the 2-point distance with a distance of 1 is in fact a squared Euclidean distance. Very, very simple, nothing complicated was said here. Just trying to get people a little more familiar with the tools here. I'm sorry for those of you who are familiar with this already. I'll get to the interesting stuff soon. Show that the following matrix is a negative type matrix, and I'll give people just 20 seconds to think about this one. Again, I think it's very important for the course of this talk to really understand negative type matrices, and in particular, this criterion that I mentioned that was sufficient for negative type matrices. Negative type matrices, again, are important to determine whether a distance embeds into squared Euclidean distance, which in turn will help us solve our core mystery that we started the talk with. So just 10, 15 seconds to think about this one. For those of you who are bored, I apologize. We'll be getting to the interesting stuff very soon. But I did want to make sure people who haven't seen this before are equipped with the necessary background. Feel free to think about this a bit. Maybe you're bored. If you're bored, you can try to think of other negative type matrices. Explore the space a little bit. And again, recall the definition of negative type matrix. It just means x transpose dx is non-positive if x is orthogonal to the all ones vector.
Well, I see that the trace is 0. Is that a start?
Sure. Well, the hint for this problem is to use a criterion mentioned before. And of course, feel free to ask any questions about what negative type means, what the background here is, and so forth. Okay, anyone want to give a solution? Any takers?
Well, this matrix has the all ones vector as an eigenvector.
That's correct. Oops.
It's the outer product of all ones with minus the identity matrix.
That's right. And then?
So then, I mean, you have just the remaining eigenvalues are like negative the identity matrix. So that has all negative eigenvalues.
Yep, that's right. This matrix is the all ones vector or all ones matrix minus the identity. So besides for the all ones vector, every other eigenvalue is -1. Another way you can see this for the graph theoretically minded people is this is the adjacency matrix for the triangle graph. And that's known to have eigenvalues 2, -1, and -1, where the 2 is the eigenvalue associated with the all one vector, and the other eigenvalues are negative. Don't worry if you didn't understand that. But basically, we're just exercising our general criterion, which is if you have a matrix and the all ones vector is an eigenvector, then all you need to do is show that the other eigenvalues are negative. And in this case, the other eigenvalues are both -1. Great. So what's the sufficient criterion for showing a distance is a squared Euclidean distance? This will be the end of the background slide here. Well, let's say you take your distances, you put them in this matrix as described in the slide. If it just so happens that you won the lottery and your matrix D has the all ones vector as an eigenvector, all you need to do now is check that all the other eigenvalues of D are negative. And then ta-da, you've shown that your distance D embeds into squared Euclidean distance. Turns out there's also a method to actually figure out what point set it embeds into, but we'll be getting into that later in the talk. All you need to know now is this criterion. Any questions so far? This is very relevant background. I'll be steaming forward assuming this. So if you have any questions, please ask now. Even if you didn't understand why we did any of this, at least what the criterion is should be very firmly fixed in your head. Any questions, comments, concerns? Any like, I got lost 10 slides ago and what are you doing? Okay, I always feel like asking the question, I got lost 10 slides ago, but anyways, we'll keep going then. Great, now we're finally done with the background slide. For Manhattan distances, we showed that any Manhattan distance embeds into Manhattan distance between the corners of a hyperbox. We also determined a general criterion for showing whether a set of distances is a squared Euclidean distance. Finally, we're going to use both of these tools to tackle our core puzzle. Why does x to the 2/3 send Manhattan distances to Manhattan distances? And here's a proof sketch. Without loss of generality, as mentioned before, you can assume the Manhattan distances are the full set of corners on some hyperbox. This is because any Manhattan distance embeds into a subset. Next, we will show that x to the 2/3 sends these distances to squared Euclidean distances. And moreover, it sends it to squared Euclidean distances on a hyperbox. So a very structured set of squared Euclidean distances. Finally, we'll note that squared Euclidean distances on a hyperbox are Manhattan distances. You can test this out for a cube, you can test this out for a rectangle. This is just Pythagorean theorem. A squared plus b squared is c squared. Squared Euclidean distances on a hyperbox are Manhattan distances. So when you put this all together, what this shows is that the function x to the 2/3 magically sends Manhattan distances to Manhattan distances. I'm sorry, that's my phone. I will stop that. Great, is the outline of the proof clear? If you buy that, like, I can prove each of these points individually, is it clear why the whole problem is solved? Questions, comments, concerns?
Just to clarify the final step, the squared Euclidean distances on a hyperbox and Manhattan distances.
Yes.
Is that because like squared Euclidean distances is just on a hyperbox is just a point? It's just like a sum of the hyperbox edge lengths. I guess I'm not sure how hyperbox helped us with that final point.
Right. Okay. So that's a good question. First, I should emphasize that this hyperbox is axis aligned. I forgot to say that. Second of all, if I have a hyperbox or a general high dimensional rectangle, how do I compute squared Euclidean distances? Well, if I have 2 points, I compute the difference in each coordinate, square that, and add them together, right?
Sure. Yeah. Okay.
So that's the same as the Manhattan distance on the same box, where if I squared each of the distances.
Okay, so the point is the point is like because the dimensions are because we're using the same offset in every dimension, we don't need to like scale or anything. We can just like remap the length of the hyperbox to make our.
Sorry, one more
Manhattan.
time. I don't think I understand.
To switch from a squared Euclidean distance hyperbox to a Manhattan hyperbox, we can just like remap all of the side lengths of the hyperbox.
Yeah, you just square all the sides. That's
okay. Got it.
Yeah,
that makes sense. Thanks.
Okay. Any other questions? Any comments? I got lost 10 slides ago. Please go back. Okay. Well, this is the overall proof structure, and the core meat of it will be showing that x to the 2/3 sends the set of Manhattan distances on a hyperbox to squared Euclidean distances on a hyperbox. And we're going to start by showing x to the 2/3 sends Manhattan distances to squared Euclidean distances. For all the people who thought the previous background was boring or simple, this is where the core of the proof is. This is like the meat and the fun stuff. So feel free to pay attention again if you were bored by the previous sections. We're going to do a proof by example, and we're going to use a 2-dimensional box. But this proof by example will illustrate the general point without losing any of the subtleties. So let's consider a rectangle with side lengths a and b, and let's say f of x is equal to x to the 2/3. Now we're just going to assign some coordinates for this, very straightforward. And now I'm going to figure out the matrix D of distances. Okay, So here, the distance is what happens when I take the Manhattan distance between two corners, and I raise it to the 2/3 power, where I apply f to it. And you can just take a couple moments to verify that I have indeed written down this matrix properly. You can just check one of the rows if you want. Okay, well, what's the name of the game here? Previously, we determined a criterion for testing if something is squared Euclidean. That's testing whether this matrix is negative type. So I'm just going to test whether this matrix is negative type. Well, magically, the all ones vector is an eigenvector of D. Turns out the eigenvalue is just f of a plus f of b plus f of a plus b. Now I'm going to claim that all the other eigenvalues of D are negative or 0. And that's going to be like the core point of this proof. Like, why would that be true? But if I have that criterion, then I know D is negative type. And then, therefore, I know that these distances raised to the 2/3 power are squared Euclidean distances. Now, this doesn't prove that they're squared Euclidean distances on a box, like I promised. But bear with me for now. This is the first step of our proof, just showing they're squared Euclidean distances at all. Is the overall proof structure clear here? Great. So we're just knee deep in proving that this matrix D is negative type. We know that the all ones vector is an eigenvector, and I claim that all the other eigenvectors of D are the columns of the 2x2 Hadamard matrix, which I've shown below. Importantly, these are the eigenvectors no matter what function f I pick. I can pick any function f, no assumptions on smoothness, no assumptions on anything, and these will always be the eigenvectors. You can verify this by calculation. But also, this is the secret use of representation theory I promised you. The secret use is that a box is symmetric under reflections about axial reflections. Okay? So that means this matrix D is, if I sort of have a permutation matrix that permutes box corners according to these reflections, that matrix will commute with the matrix D. And it turns out any matrix D that commutes with these permutation matrices will have the eigenvectors being the Hadamard matrix.
Tim, just
Yes.
1 second. The last sentence of your slide is not visible. What does it say?
I basically just said it in words. All I'm saying is that if you have any, 4x4 matrix that commutes with these axial reflections or the permutation matrices corresponding to the axial reflections, the eigenvectors of that matrix will be the columns of the Hadamard matrix. Again, if you're not versed with your group representation theory, you can just verify this by computation. It's not that hard. But I claim this is sort of part of a general picture, which has a very nice, beautiful theory about symmetries and group theory and so forth. Great. So once again, we're knee deep in showing D is negative type. We know D has the all ones vector as an eigenvector, and all the other eigenvectors are columns of the 2x2 Hadamard matrix. So let's just figure out what the associated eigenvalues are to show that this matrix is negative type. Well, let's just take the eigenvector 1, -1, 1, -1. Okay? And we know this satisfies D times that vector is equal to lambda times that vector. Well, just using a little bit of math, which isn't too complicated, this can be computed, this lambda can be computed by evaluating the first row of D times your vector V. What is that going to be? I take my first row of D and multiply it by 1, -1, 1, -1. Anyone? Just come at me.
Minus f of a, minus f of a plus f of b minus f of a plus b.
That's right. Okay. Now, when f is equal to x to the 2/3, why would this be negative? And again, if you understood nothing about this proof so far, you can come back here. All I'm claiming is that this expression I've written down on my last bullet is negative when f is x to the 2/3. Any takers?
Is that the triangle inequality?
Yeah, it's just a triangle inequality. but you can also see it using something called the fundamental theorem of calculus, where you can verify that this expression is equal to this integral. And x to the 2/3 is a positive derivative, and so I'm integrating over a positive function and taking the negative of it. Just a fancier way to see it, you can see it through triangle inequality. But this integral method will generalize. Okay, I'm going to do just one more computation. Once again, I'm knee-deep in proving this matrix D is of negative type, aka all the other eigenvectors that aren't the all ones have negative eigenvalues. And the eigenvalue corresponding to V equals 1, -1, -1, 1 is equal to f of A plus f of B minus f of A plus B. And once again, I can figure that out just by multiplying the first row of D by this vector. Why is this always going to be negative when f is x to the 2/3? I'll give you a hint. Turns out that this expression is equal to the integral of the double derivative of f over the a by b rectangle.
That's negative again because 2/3 is less than 1. So if you take a derivative twice, then it becomes negative.
Exactly. X to the 2/3 is a negative double derivative. So if you integrate a negative double derivative over some region, you're going to get a negative number. There are other ways of seeing this. This is just a classic use of convexity as well. But you can see that this eigenvalue is always going to be negative. So what did we prove here? Well, I skipped one of the eigenvectors, but don't worry about that. The computation is straightforward. We showed that our matrix D has eigenvector of the all ones vector, and all the other eigenvalues are negative. And we did this because matrix D had a very structured eigenbasis, and you could just straight up compute the eigenvalues. This means that it's negative type. That means that the original distance is squared Euclidean, and thus we've given you a self-contained proof that x to the 2/3 sends the Manhattan distance to squared Euclidean distance. What properties of x to the 2/3 do we use? We use that its derivative was positive and its second derivative was negative. The general property you'll want to use for higher dimensional boxes is the first derivative is positive, the second derivative is negative, the third derivative is positive, the fourth derivative is negative, and so forth. That's what a Bernstein function is. But don't worry about that too much for now. Great. So by using this beautiful matrix criterion, we've shown that x to the 2/3 sends the Manhattan distances to squared Euclidean distances, but that's not what I promised you in the proof outline. I promised you that it should send these Manhattan distances on a box to squared Euclidean on a box. How do I do that? Well, once again, I'm going to use the amazing eigenstructure of D. And I'm going to show this by backing out the actual embedding. Here, we're going to take a quick interlude. This is work that was known before. This is also work from Schoenberg in 1935. Very beautiful. Given a squared Euclidean distance, how do I actually find the points that realize that squared Euclidean distance? Right? I just give you a set of distances. How can I find points such that, the n choose 2 distances between those points are the distances I want? Well, let's say you have your squared Euclidean distance in a matrix D. And by the way, when I say squared Euclidean distance, I just mean Euclidean distance squared. You can find the matrix of dot products by computing the following kind of weird looking matrix. Just take my word for it that this works. What you'll do is you'll take pi to be the projection matrix off the all ones vector, and you'll pre and post multiply your matrix D by pi. And then you'll multiply by -1/2. Once again, pi is the projection matrix off the all ones vector, and you can explicitly compute it because it's I, the identity, minus the all ones vector divided by the dimension. But don't worry about that too much for now. Finally, I can show that any matrix P with PP transpose equals M has row vectors which realize that squared Euclidean distance. So basically, if I wanted to figure out a set of points that have the squared Euclidean distance I want, I'll write M equals -pi d pi over 2. I can just compute that using a computer in polynomial time. And then I can eigendecompose M, or do like any SVD composition to find some point P where PP transposes M. In this case, the rows of P will be those points that realize a squared Euclidean distance. Just take my word for this that all of this is true. This is not that hard to verify, but it'll take a little longer than the scope of our talk. So TLDR, given a distance matrix, you can compute the points that realize it. And all we're going to do is compute that for our structured distance matrix D. Well, let me just give some brief intuition for this. This slide is not super important, but if you're really curious why this was true, I'm going to go into it. Let's say J is the all ones matrix and P is the matrix whose ith row is Pi. Let Pi be the points such that, the ijth distance is the difference between Pi and Pj squared. So these are the points that realize our squared Euclidean distance. Just going to expand it out a little bit. And if you just do the math, and you can take my word for this here, this is a very simple calculation, you can show that your distance matrix D is equal to the following complicated formula. You basically take a diagonal matrix where your diagonal elements are Pi squared, multiply by J, add this next term, and subtract 2 PP transpose. And that just follows from expanding, what Dij is. Very straightforward calculations. I'll leave that for the reader. Recall how we defined M. And what does pi do? Pi crushes J. So when you pre and post apply J to D, the first two parts of the sum just completely evaporate. And you're left with PP transpose. You're also left with these pi's here. But if you assume that your p's are centered at the origin, then this is just equal to PP transpose. Don't worry too much about this slide. This is just for the people who are interested in why the claim I made previously was true. All you really need to know is, given your matrix D, how do I find a matrix, the original point set P? And it's just a matrix problem. Any questions on this part? We have about like 5 more minutes in this talk, so please ask your questions now. Questions, comments, what's going on? Everything clear to everyone? All right, I'm going to assume things are either clear or you got lost 10 slides ago. Great. So all we're going to do is say, try this on our matrix D. Okay. We know that our matrix D encodes a square Euclidean distance. So what are the points that realize it? Well, we know what the eigenvectors of D are. They're equal to these matrices as follows. And we know that D is equal to this formula here. Why is that? Well, D is a symmetric matrix. All of its eigenvectors are orthogonal. And this is the canonical way you decompose D into like its eigenbasis. This is like the SVD decomposition. Don't worry too much if you don't know why this is true. This is a very standard fact in linear algebra that has nothing to do with our structure of D. It's just true for any matrix with the appropriate eigenvectors. And I claim that the matrix M, this magical matrix of dot products, is equal to negative pi d pi over 2. That was something that we asserted previously without proof. Here, pi is the projection matrix off the all ones vector. What is M? Well, it turns out all this pi matrix does when you apply it to D, pre and post apply it, is it crushes the first term. Like it crushes lambda 1 times H1 transpose. Because pi projects everything off the all ones matrix, and all my other eigenvectors are already orthogonal to the all ones matrix. So it turns out M can just be written as this formula. All I did was take D, strike the first term in the sum, and multiply it by negative 1/2. This is sort of routine calculation. I'm sorry that there's a lot of math in this, but just know that nothing too complicated is going on. I should say, just to give a little bit of intuition what this matrix M is. Well, besides for being a matrix of dot products, pi d pi has the following property. If I input a vector, I'm going to first project it off the all ones vector. Then I'm going to apply D, and then I'm going to project my results off the all ones vector. Just a maybe more intuitive picture of what M does. Great. I have my matrix D, which I know has a certain eigenstructure. I know that M has another, a very similar formula in terms of the eigenstructure. And now I claim that you can decompose M as PP transpose, where P is the following matrix. Now, I claim that if you understood nothing in the entire talk, you can at least verify that M is equal to PP transpose. So I'll just give people like 20 seconds to verify that this is the case. Again, no need to have understood anything that led to this point. Try to show that M is equal to PP transpose. During this time, I'll also just state what our overall strategy was here, because I know we got very deep in the math. We showed previously that x to the 2/3 sends Manhattan distances on a box to squared Euclidean distances by using our magical negative type criteria. I am just trying to figure out what points realize that squared Euclidean distance, and I'm going to claim they all live on a box. Right. So what I did was I gave you an unproven formula for how I back out the points that realize the Euclidean distance. If you buy that formula, right, just take my word for it that it works. You can calculate from D, you can sort of calculate this matrix M, which is the matrix of dot products. Then you can decompose M as PP transpose, and it has this very nice formula here. Note that each of these lambdas, as mentioned before, are negative. So each of these square roots is in fact a real number.
Question.
Yes.
I feel like in this entire proof, you have not used 2/3 is a 2/3. You've just used this between 0 and 1.
Yes, that's correct.
So where does the 2/3 come in?
2/3 is not magic. You can use anything between 0 and 1.
Oh, okay.
Yes.
Even in general dimension.
Yes, in general dimensions, anything between 0 and 1 will work. Okay. Well, even if this made no sense, the high level picture that I really want you to take away is that our distance matrix D, when you have a box and you raise them to the 2/3 power, this matrix D has really structured eigenvectors and really structured eigenvalues. And from them, you can mine all sorts of valuable information. That's the high level 1 second soundbite. So the proof recap, once again, you can just read this. I think we went over it enough times. But overall, points live on a hyperbox. That's an assumption you can make without loss of generality. Apply 2/3 to them, x to the 2/3 to each distance, you get a squared Euclidean distance. Because the eigenstructure of my matrix D of distances was so nice, I could prove that they were squared Euclidean distances on a hyperbox. Finally, we knew that squared Euclidean distances on a hyperbox are Manhattan distances. And you can verify that for yourself if you don't see it right away. That's sort of a cute 5-minute exercise. Thus, putting this all together, x to the 2/3 sends Manhattan distances to Manhattan distances. And this is the full proof that I promised you. Again, key things to note, x to the 2/3 was important because it had alternating derivatives after the first one. The box was important because it had these very nice symmetries that allowed for this great eigen decomposition, secret use of representation theory. And there was a lot of machinery we needed about how to tell whether points were Euclidean distances or squared Euclidean distances, and if they were, how to back out the embedding. I should just note here briefly that there's no good criterion for determining whether points are Manhattan distances straight off, which is why we needed to go through this Euclidean distance rep anyhow. Determining whether a set of distances in Manhattan is an NP-hard problem. Great. Finally, I'll just cap off this talk with saying what a Bernstein function is, okay? I promised you at the beginning that a function stands a Manhattan distance to Manhattan distance if and only if it is Bernstein. The proof I showed you can show one direction, that any Bernstein function works. The other direction is a little bit more complicated, but it's in our paper, and it's actually not that bad. But what is a Bernstein function? Well, it's a positive valued function, or non-negatively valued function, whose derivative is positive or 0, its second derivative is negative or 0, third derivative is positive or 0, and so forth. Right? And this is all on positively valued x's. Let me just give you an example of a Bernstein function, because I think the abstract definition isn't great. Can anyone think of examples besides x to the 2/3? I just want a function whose first derivative is positive, second derivative is negative, third derivative is positive, and so forth when I input positive numbers. I think one of them was already said, x to the s for any s between 0 and 1. Anything else?
Like a lot of polynomials could work. Like
A lot of polynomials.
Like any linear function. Sorry.
Yeah, any linear function, right? Like a linear function.
Not any linear function. Like, because then your derivative would be, your first derivative would be positive, which we want our first derivative to be positive.
Yeah, you want your first derivative to be positive.
Okay, so just to be clear, there's no requirement on the values. It has to be positive valued. Okay.
Yeah.
So like any positive linear function would be good enough.
Yes, that's right.
But that's because you can spell space. Sorry, go ahead.
Sorry, I just want to say we had someone in the chat suggest 1 over x.
Let's see, 1 over x. Let's see. The derivative of that is, so that doesn't quite work because the derivative is negative.
Oh, minus 1 over x.
Right. You'll have to shift it a little bit. So, you can do 1 minus 1 over 1 plus x. 1 minus 1 over x basically also works. It just has this weird divergence property at 0. I also listed another function, which is 1 minus e to the negative tx. Log 1 plus x also works. And any positive linear combination of the above also works. And as I think Isaac mentioned, there should be a suite of polynomials that may work as well, but I haven't verified that in depth. Right, but this is a suite of Bernstein functions. And Bernstein functions turn out to be super central to whole areas of math, but I won't go into that now. I'm missing a slide in this talk, but I'll just say it out loud. And this is just the final slide that I'm going to go through, which is this question, I think, was in my opinion, was an interesting use of representation theory. That's how we got these structured eigenvectors of our matrix D in order to prove a theorem about metric embeddings. But there's a very general question that you could ask instead of the question, what function send Manhattan to Manhattan? I could ask you, given any two metric spaces, M1 and M2, which function send M1 to M2? And to my knowledge, this problem is very underexplored. Like which function send L3 to L5? I have no idea. One thing I've done with Professor Miller and a couple collaborators is we can actually do the following. And this is unpublished work so far, which is we can find a full classification of function f that send any of tree distances, effective resistance distances, or Manhattan distances to any of squared Euclidean distances and Manhattan distances. What does that mean? If I wanted to classify all functions that send effective resistance distances to squared Euclidean distances, I could do that for you. If I wanted to find any functions that send tree metrics to Manhattan distances, I could do that for you. And the secret is these are all just Bernstein functions. Bernstein functions are the only thing that works. Nothing else works, and all Bernstein functions work. However, there are still many extensions here that we don't know the answer to. Like what functions send effective resistance distances to effective resistance distances? I'm a spectral graph theorist, so I like effective resistances. What functions send L5 to L2? What functions send distances on a line to, distances on a tree? Lots and lots of open questions. The final thing I want to say, the very, very last open question, is that the framework we sketched out here depended on this structure of the box. There was a very nice group of symmetries. Theoretically, you could do this for anything that has a nice group of symmetries. You can, in fact, redo Schoenberg's original work in this criterion by using this, because Schoenberg deals with functions that send Euclidean distances to Euclidean distances. Euclidean distances have a very nice rotational, reflectional, and translational symmetry. You can redo all his work using our framework. But other questions that I'd love to figure out is, let's say you have a crystal lattice. What functions send crystal lattices to Euclidean distances? What functions send, a tree? An infinite binary tree has a lot of symmetries. What sends infinite binary trees to, I don't know, like Euclidean distances, right? There are what sends icosahedrons to Manhattan distances. There are a lot of structured distances that have very nice symmetry groups, icosahedrons, crystals, infinite trees, generalized polytopes, any graph with a vertex transitive group symmetry. I would love to figure out a general criterion for function f that's in any one of those to say squared Euclidean distance or something nice like that. Thank you very much for coming out to my talk. I hope you learned something from it. I'm sorry, I think I went a little bit over time. And I'll take questions, anything you want right now.
Yeah, first let's thank our speaker.
Questions, comments?
I had a question.
Yes.
So you mentioned that previously work like this had been used to develop kernel methods. I'm assuming they were kernel methods for like squared Euclidean, like for L2 loss functions. Can you use these methods to get nice kernel methods for L1 loss functions, or is there still more work to be done?
So unfortunately, I'm not entirely familiar with the loss function literature.
Okay.
When I said kernels, I mostly meant that I think there's a very popular method in machine learning that uses the Gaussian kernel, like e to the negative Euclidean distance squared, as like an inner product. Is that what you're referring to?
I was just referring to the thing you mentioned earlier in the talk. I might have misinterpreted it. Yeah.
Okay.
So if you wanted to like replace your Gaussian kernel with like some L1 style kernel, this would allow you to do that?
That's correct. And while I didn't say it here, our results give us a general criteria, a classification of all possible kernels with which take L1 as input. So the equivalent of the Gaussian kernel would be e to the negative Manhattan distance, not squared, just the Manhattan distance.
Right.
Any other questions, comments? I can go back to certain slides to help people catch up.
At the very end there, you said you said something about other cases of this thing, and you found that, you know, for example, functions that have you said something along the lines of resistance resistances to Manhattan distances or whatever. That was also Bernstein or whatever.
That was also, yes, that's correct.
Do you know of any case where the answer isn't or can't be Bernstein?
So I know so there's a classic example that Schoenberg worked out a while ago with this guy von Neumann, who you may have heard of. But he asked the question, what functions send lines? So if I just take points on a line and take their distances, what functions send lines to Euclidean distance or to the squared Euclidean distance? There, it's known that the class of functions is much more general than Bernstein functions. Bernstein functions will also still work, but the general class of functions is way richer. Also, what functions send effective resistances to effective resistance distances? I do not actually think Bernstein functions work here. I tested out a bunch of Bernstein functions at some point, and not all of them worked.
So in fact, you know the answer isn't all Bernstein functions.
Depending on which problem you pick, like if I pick effective resistance to effective resistance, I know that it's a subset of Bernstein functions, but I don't know what that subset is.
Okay.
It's a strict subset. Any other questions? Comments? Any parts of my proof that were maybe a little unclear that you'd like to revisit? Just a couple more seconds for the stragglers who are shy to say a couple words. Okay, well, if there are no more questions, I think my Andrew ID is TZ Chu. Feel free to email questions my way. And just as a last takeaway, I hope I at least gave you some intuition for why x to the 2/3 sends the Manhattan distance to Manhattan distance, some belief that this is at least a part of a richer theory about general metric transforms, and hopefully it at least inspired you to look a little bit into this, like into my paper, right? Like, why are these matrices D so structured? Why do they have such great eigenvectors and so forth? So without further ado, thank you all very much for coming out, and thank you. Thank the organizers for organizing. I greatly appreciate it.